Hello everyone. In the third episode of our series on STL algorithms, we will continue our journey. We covered numeric algorithms in the previous episode. Moving forward, we will be covering further into the land of queries. So we have very simple querying on properties of a collection, all of, any of, none of. These three algorithms return Boolean values, and basically all of tests if there is the predicate is true for all of the elements in the collection. Any of will test if the predicate is true at least in for one of the element in the whole collection, and none of will return true if the predicate is false for every element in the collection. So moving to code, let's move to the code. So first we will try any of. Let's prepare a vector of 10 integers, and every element of this vector will be less than 10. So we can check that. Okay, is all elements less than 10? We can ask that question and answer that question using the value returned by all of. Sorry, the name is all of first, any of will do next. All of v vector, so always where algorithms take range all the time like we have seen so far. And now the predicate, right? So we want to check whether every element in the collection is less than 10. So the predicate will be the element that is in the collection. We want to compare it and check if x is less than 10. If this returns true, then for every element it will return true. So let's check that what is the output for this. So it is saying all elements true. Yeah, printing 1 for true. So all elements are less than 10, so that prints true. So let's convert this vector into elements of all even numbers so that we can check other two algorithms. Execute lambda onto the so remember this lambda element is copied by value here. So even if we try to modify it, it won't work. It won't update the collection. So what we need to do is we need to use the reference. Okay, non-const reference. Now it is x is an alias of the element to the collection, and if we modify through reference, that original value will get updated. So therefore, make sure that we understand why we need a reference over here. All right. Now let's print this vector, and we should be seeing, let's comment this out. We should be seeing the vector of even numbers, and then here is it, and then we can see if any of this vector is odd. Any element is odd, so any of v dot begin v dot end, does it meet this predicate of it being odd? So if it is odd, it should return true, right? So x percent 2 is a check for even. So if it is true, it should return false. So x percent 2 will be 0 in case of even, and the predicate should return false. So we simply return whatever x percent 2 result is. So now the answer to this question should be 0 because none of the elements is odd. So let's check that. Any element is odd, false, 0. So which is true because we have vector of even elements. And let's convert this one value, maybe fourth value, into an odd number. Okay, and now let's check if the same value, uh, any of algo returns true this time. So after setting the value 4, we can see that any element returns true because at least one element is actually odd now. And now let's comment this out again because we want to keep the even vectors, and then we can say none of, right? So none of the elements is odd, so that should return true. Okay, none of the elements is odd should return true. Actually, no elements is odd, so that is an affirmative. So none of v dot begin, v dot end, and the predicate will be, we want to return um, the predicate is the check for evenness. So none of the elements is odd. So x percent 2 should return true if it is an even, right? So let's check. Or we can modify the sentence actually that all elements are even, right? So that will also be same thing. All elements are even. If none of the element is returning false for x percent 2, then all elements are even, right? So it's the negative of none of. So let's see. We can put some end lines here. So these are easy to follow algorithms, but quite useful in problem solving to find out things. So you can say all elements are even, which is returning true because we commented out the only element we tried to add odd. So this was about the um, simple querying on the property. Now, next we move on to further querying on a property on two ranges, multiple ranges. There are two ranges, and we want to query about some properties on two ranges at the same time. So equal is the first one. Equal must be that the two ranges are having exactly same elements at the same locations. So it should map one to one. It should be equal one to one, as the figure is suggesting. Then we have is permutation. Is permutation will return you true in case the elements in the collections are permutation of each other, some arrangement of each other. They might be shuffled, but they all of them are present in both ranges, right? So the ranges are some permutation of each other. So it's very useful to um, could be very useful algorithm to know, given a range, is there any other range, a permutation of the other range. That means we want to check if any element of our collection is existing in the other collection, and exactly in the same number of times. The frequency is also same. So it is permutation is the right algorithm to do that. Then there is a lexicographical compare, which basically means that it will compare the collection and report the one which is coming first, as if based on whether it will come first in the dictionary. It is used obviously for string comparisons, right? And it will return true not based on the size. So sometimes lexicographical comparison will really help, especially in case of name comparisons, etc. Then we have a very interesting algorithm, mismatch. So what it does is basically it will start scanning and matching the elements of the two collections. Okay, and then where the first mismatch occurs, it will tell you where that mismatch is. Okay, so it will return a pair of iterators. The first iterator will point to the element that got first mismatch on the left collection, and the second iterator will be pointing to the second collection's element, which from where the mismatch really started. So this is um, interesting algorithm to use. For example, in situations, if you have observed in our, we do um, when we go for money deposit and we hand over the cash to the depositor, they run the money through a machine which not only counts it but also checks for the features on the notes, the currency notes, and see if there is any suspicious duplicate or fake currency note, right? So that could be an algorithm inside it where mismatch could be used. You have an array of the features of a real note, for example, the color code, the silver bar through the note, and stuff like that. So those features could be listed in the first collection here, and the other collection will list the features read from the current node which is under scan. And then you can run this mismatch algorithm, and if it returns any of a valid iterator to any of the collections, that will tell you that there is a mismatch and which feature exactly did the mismatch, right? So that can be very useful information, because then you know that there is this note is a fake note, and then obviously other features should also mismatch, but if they pass, then we would that is a matter of further investigation, like how come that print happened so fine that it matched the first few features of the real node, right? So that kind of application can have an embedded C++ program where we could use mismatch STL algorithm. So interesting algorithm, I found it. So let's go through the code examples for these algorithms now. So first algorithm is equal and also is permutation. So let's prepare two vectors. First one, second one of the same size, right? Remember, our prepare vector returns a shuffled vector. So let's check if the two vectors are equal. and is permutation, both, right? So we will check cout is equal, and then we will um, call equal on two vectors. So we begin, we end, you begin, you end. Okay. Okay, so we don't need to pass the end of second vector because it is equal function will return. You will expect both vectors to be of equal size anyways. Okay, so and then let's check if um, now we shuffle them once, and okay, so without shuffling also is permutation also should return same thing, is permutation. Sorry, is permutation, and it will take two vectors, begin, v dot end, u dot begin, and that's it. Let's print the result. Okay, so is equal should not be returning true, and is permutation should be returning true, right? But we see that is equal is returning 1, so that means our shuffling basically is returning the same um, shuffle every time. Basically, what if we see the definition of this function, we have used this default random engine. I think we are not passing it anything, so every time it is called, uh, it will start from the same permutation and shuffle it accordingly. So if we call prepare vector once, it will shuffle, and if we are calling it again next time with the same set of elements, it will shuffle them in the same order because it is called again once for the different set of element, right? So two separate steps, and first step of those is same every time. So that is why we are seeing the um, same equal is also returning true because their order is same, right? So it is not really shuffled. So let's shuffle one of the vectors again. U dot begin, U dot end. Okay, and um, it needs again the default engine, uh, random default engine. Sorry, random default random engine, and then it should do the trick. Now is equals hopefully will not return true because we are shuffling the vector again, and that will take the second permutation, so it should be different from the first one for each of two. And is permutation should still return true because the number of the elements is actually are same in both vectors, just their permutations are different. So let's check that. So now it is fine. Is equal is returning 0 and is permutation is returning 1, right? Okay, so that is permutation. Now we have lexicographical compare. Let's set one string str1 to some name, Albastra Nicoli. or something, and then the other name, let's pick a smaller name, maybe Aisha M or something. Okay, now we see that string 1 is larger than string 2 in terms of size, but if we were to put these two now names in dictionary, string two's name will come first. So our lexicographical comparison will return true for str2 being bigger than str1. Okay, so we'll say cout um, lexicographical comparison between str1's begin and str1's end, and compare it with str2's begin and str2's end. So it returns true lexicographical compare if the first argument is going to come first in the dictionary, then str2. But in our case, it should be the opposite. So we should see the value 0 coming and getting printed over there. Okay. So let's see if that is printed as that, as what we expect. So the last value should be 0. So it is 0. So we can see that it is comparing them as per the alphabetical order, not the size of the collection. So it is an important function, very useful in names and other string handling places. So we have the mismatch now. Let's take the two vectors and sort them, u and v. Okay, v dot begin, v dot end, and also sort u. Okay, and now let's see if they do match or mismatch, right? Using mismatch. Obviously, we have same element, same size, and after sorting they will match, right? So mismatch will return false. So that means if we um, check the result, it returns mismatch will return the pair, right? So result will be a pair mismatch, and it will take two collections, v dot begin, v dot end, and u dot begin, u dot end, right? And then um, okay, sorry, I keep making this mistake again and again. Only one starting iterated for the second argument is enough. So now if we check the result is a pair. So first of the result is the iterator pointing to the v element, which is a mismatch, and if it is pointing to um, v's end, that means there was no mismatch on the left side, as well as first result second should also point to u's end, right? So if both are pointing to each vector's end, we can say that it is a um, match, right? Because mismatch returned both iterators pointing to the end of the collections for both. So it is a match. And if not, then we can say it is a mismatch, right? So in our case, in this case, we should see, one second, we should fix the error first. In this case, because the vectors are both sorted, match should happen. So match should be printed. Now let's shuffle one of the vectors. Okay, and see what is the result. Hmm, you got and then we need that the default random engine entry over here. Now, if the result, and we need to run mismatch again, and basically use the same code here. Okay, so after shuffling, we should see a mismatch. Mismatch should return some element not to pointing to the end. It should point to some iterator position where the mismatch is happening first. So we are expecting match and mismatch as the result of this program execution. Let's try that. Error result is okay. So we need to just reuse the result rather than trying to create another variable. So you can see match when we sorted the vectors and then mismatch when we shuffled one of the vectors. Okay. Moving further, we are having algorithms for searching for a particular value, and these are really useful algorithms because searching is one of the most common operations that we need to do in many problem solving situations on a collection. So we are going to go through these algorithms that STL provides us, which help us find some particular value in a collection. So the when we are performing a search, the collection on which we are performing the search might be sorted, or it might be not sorted. So depending upon whether it is sorted, some algorithms will have that prerequisite, but some algorithms will work on not sorted collection too. So the first algorithm is find. So you give it a value and it will tell you the first occurrence of that collection is occurring at what index. It will return an iterator to that index. And if you are to find the index, you can minus the begin of that collection from that iterator, and you will get the index of that value where it is occurring. Adjacent find will tell you the first occurrence where two values of the same um, thing that you pass to adjacent find are occurring back to back, like continuous two existence of two values, like a pair. It can obviously work on sorted collection also, which I think will make more sense, so that all the values can be there at single group in a single group, and then you can probably see adjacent find to check if there is any duplicate in that collection. But in case it is not sorted, then still you can see if anybody any collection or any element has same element following or before it. So it will return the iterator to the index of the first element. Okay, that is adjacent find. Equal range, uh, and we are now moving towards the sorted algorithms, meaning the prerequisite is that the collection should be sorted. So if I am looking for a particular element, equal range will return me the collection, the index or the iterator it will return me a pair actually. So um, it will return me the lower bound, the first pointer to the first match, and then second element of the pair will be the upper bound, the pointer to the element just after the last match, right? The first element after the equal range, after the range is found. So equal range gives me both lower and upper bounds. Okay. If there is a single element, obviously you can use equal range also to find that element. Um, it will return you the pair and point to the first element itself, and the upper bound will point to the next element. So you can use the first element to know the location, the iterator to that. But if you don't want both upper and lower range, you all you want is to find the lower bound. So we have the STL algorithm lower bound for that purpose. Lower bound will return you iterator to the matching element. Okay. Upper bound will return you the iterator to the next element, which is a mismatch after the range is found. Okay. And then binary search will simply return you true or false. It will tell you whether this particular object is part of the collection or not, but it will not return you the iterator to that object. Okay, it will just simply tell you yes, it exists. If it exists, then probably you can go for lower bound or equal range to find the actual index of that particular object. Okay. Um, then we have searching for a range. Um, if if you have a sub one smaller collection, like a collection which you want to search for inside of a bigger collection, we have few algorithms for that. Maybe you want to search whether any one of these elements is existing in the target collection. For that, find first of is the algorithm to use. It will check the occurrence of any of the elements here. For example, here orange or yellow is existing in the target collection, so it will finish with this iterator. Okay. Search, on the other hand, will actually look for this complete range inside of the target collection. So blue, gray, orange, blue, gray, orange. The first occurrence of this collection will be the find of the search. Okay. Now, if you want to search for the same collection but want to start from the end, you have you should have probably search end, because search is the name of the function, and search end would probably mean start from ending part. But unfortunately, the name of the algorithm is find end. Okay. So if you are looking for a range, you want to find the last occurrence of that range in a collection, you will use find end. If you are looking for a range and you want to search for the first occurrence of that collection in the target collection, you will use search. Okay. And then we have three algorithms for searching a relative value. We have a collection. Max element will return you the maximum value element iterated to that element where the maximum value is existing. Min element will return you iterated to the element where minimum value is existing in the collection. And min max element will obviously return you a pair where both the first element of the pair will be iterated to the small or minimum element in the collection, and second of the pair will be pointer or iterator to the maximum value of the element. So these are our searching for a value algorithms in our STL, and let's go to code and do some hands-on. Let's start with find. and this is a non-sorted collection. It doesn't need a collection to be sorted. Um, let's prepare a vector. Let's start from 10 this time. So we have starting element as 10 and total number of elements will be 10. So the vector will look like 10, 11 all the way till 19, I guess. Then um, let's search for a value 15. Search value s is 15, and then return, we should find where the 15 is existing, right? So print vector v, and let's print the index where 15 will be existing. Remember, prepare vector will shuffle the vector, so it may be at any place. So let's find it. So cout index at, or we can say v, and index will be find. What do we want to find? Where we want to find? We want to find in this range, in whole of the v vector. So and then begin and end. And what is the value we want to find? We want to find s. Okay. If it finds it, it will return an iterator to the index of the element, right? And that iterator, if we minus v dot begin from that iterator, it will give us the index of that element, right? So that is the number we want to print, and then we want to close the bracket, and then we want to say star. We haven't saved the iterator. Let's move it out. Maybe we'll save it then. Auto find iterator, and here we can see then find iterator minus v begin, and then wherever it is pointing to, um, equals to goes inside of it. Okay, so let's see how find iterator works. Find algorithm works actually. So v4 is 15. 0, 1, 2, 3, and 4. The index at which found 15 number is 4, and you can see that v4 is 15, which is true. Good. Now let's move to adjacent find. So for adjacent find, um, let's, so because we know, what should we do? How do we put two values are the same back to back? Let's do that. So we can say we, after we get the vector, let's say we want to have value 4 and value 5 equals to 3. Okay, then let's find auto adjacent iterator, adjacent find. We want to find in the begin and whole of the collection, and we want to find value not s, but we want to find 3. Okay, so s is 3 now. Let's modify it to, and let's see what it returns. So um, let's return the index only, iterator minus v dot begin, and we'll print the vector as well. and the vector the begin should return us uh, first. Let's fix the error. Which one? uh, we don't begin. Where is the error? The error is in template function adjacent find first, last, and the predicate. um, the predicate. Just a second. The adjacent find actually takes a predicate. It does not take a value. But if you don't pass a predicate, it will take the default predicate of equals to sign, and it will basically detect the occurrence of first adjacently occurring same values in the collection. Okay, you don't need to if you don't pass it a predicate, it will find any of the such pair, right? The first pair which is occurring of the same value in the collection. If you pass a predicate, then it will obviously check for that, right? So let's try finding this. um, in the default collection, it will check. Now we have set the 4 and 5 indexes. The elements of fourth and fifth index will be equal to 3. So the iterator should return the index pointer to fourth element, like the fifth element, fourth index, and therefore this should return us the value 4 here. So let's check that. So you can see that the occurrence of this first pair, matching value pair back to back, is occurring at fifth number 1, 2, 3, 4, 5, which is fourth index. So we have the fourth index printed, right? So if we were to pass a predicate, we equivalent predicate will be it is going to compare two elements of the collection. So we'll have two elements, and then we just simply return if x true, if x equals to y. Okay, and it should basically return the same value. It should do the same thing like so. So adjacent find is quite useful in finding the first duplicate in a collection, and then you can use the predicate to define the criteria of adjacency, right? The default criteria is that the value of the two numbers is same. Okay, by value they should be same, but predicate allows you to define any adjacency criteria. Okay, so um, that was adjacent find. Now let's move further. We want to now try binary search, right? So let's sort the collection. We have got this vector, and let's not print set anything for adjacent find, and let's comment this code as well and move for search. So binary search requires the um, collection to be sorted. So we are reaching the the set of algorithms which require the collection to be sorted. So our prerequisite is um, sorted collection. Okay, so search. First we'll do the binary search after sorting. So let's sort the collection first. Sort b dot begin, b dot end. Okay, now our collection is sorted. Remember our vector is from 10 to 19, right? And um, let's comment that out as well. Let's see if it finds the S in binary search. Binary search in the whole vector, and we want to find S, which is set to 15, and it should return true or false based on whether the value is existing or not. So since 15 is existing, it should show 1 as out for this. So you can see it is showing 1. It is not telling us where does it exist, right? So that is the job of other equal range and lower and upper bound guys. And for that, let's create again a 3 value range, v7 and v5 as same values as like S, or basically 15. Okay, so now we have 5, 6 and 7 as same values, which is 15, right? Now equal range will return us a pair. So equal range will search in the whole of the vector, and we are looking for S 15 value. It will return us a pair, equal pair. The pair will have first as its lower bound, right? Iterator to the first value which is occurring, um, which is equal to S in the collection. So cout, um, let's try that. The index equal pair dot first minus v dot begin. That is our index. And star equal pair dot first will be the value. Okay. And then the next value will be second minus v begin. Okay, second value minus v begin and minus one more time, because we want to, the second is one past the range value. Okay, so let's see if that works for us, and then we will say second, and let's print the vector here. Okay, let's see how it goes. So we can see the v5 is 15. Okay, so 0, 1, 2, 3, 4, 5 lower bound of this collection where this equal range is found, and upper bound v7 is 18. So v7, it should be v8 because we minused it in the index but did not minus it from here. So the correct way would be star of second minus 1, right? Because we did a minus 1 here. So it is giving you the equal range occurring, the range or the value S is found at first index returned by equal pair first, and second it occurs till this value. Okay, so if we see the print now, it should give us the right value. Now you can see that it is occurring from 15 to 7. Three values in the collection are equal to 15. So that is equal range. But like I said, we don't need to use equal range if we just need the lower bound. So we can see the lower bound as well. So we can say cout lower bound of from whole vector which is sorted, and we want to look for S value, right, 15, and we want to minus v dot begin from it, and that will be our index. And then we can say that value, and we want to print the value because we'll otherwise have to take the value again in the lower bound. So just let's print the index only, and we can print the upper bound as well immediately so that we don't have to run it twice. Upper bound, okay, it will basically return the same values as our equal range but independently, lower bound for lower, upper bound for upper. So you can see that index 5 is same, and here we had minus 1, so minus 1 if we remove that will be 8, so here 8 also, so they return the same index basically. Okay, and now we move to searching in the range. Okay, so we have a vector already um, that we have been using. So searching in range. So let's prepare a smaller vector where we want to do the search. So now we don't want to put this, and let's what we can do is we can prepare another vector. Basically v equals to prepare vector 10 10, and then we have smaller vector subvector from 12 only for 3 size, so it will be 12 13 and 14. Okay, and then we need to um, search for any of these, right? So let's do find first off. So these algorithms returns iterators, so find first off equals to find first of v dot begin, v dot end, and then we want to use the uh, range where which range we want to find in, so that is sub range. We want to find from the whole of the sub range, right? So we are looking for any of these values in the vector v. Okay, and it will point us to the first index where this match happens. So cout index will be ffo minus v dot begin. Okay, So let's see what is the value that gets printed now. Let's print this vector. So you can see it is returning 0. There is no 12, 14, yeah, right. So 14 is also part of this subvector. So 14 is occurring at the first page itself. So therefore, it is returning as 0. Okay, that is fine. Um, Now we check for, let's see, we are now going to do the search. So for search, let's sort the vector. Sort v dot begin, v dot end. Okay. Now we want to search for the vector sub. We also want to sort the subvector. Only then we will be able to find the search, because subvector is shuffled, right? And if we sort the vector v, the subvector will be shuffled and it won't be matching in the range in the v vector. So if we don't sort it, it won't match. So let's see if it shows us what. Auto search iterator. Search in v.begin to v.end. Search for um, sub.begin and sub.end. Whole of this range, search in that, and let's say cout search iterator minus v.begin. Okay, let's see what it returns now. Because the subvector is shuffled, it may not find the range as such, because unlike find first of, which is looking for just one of the whole sub element of in the sub range, it is looking any of the element which is in the subrange, looking for that in v. But search will look for all of the element in the same order, right? So it is likely to return us the end of the vector, maybe 10, I guess. The index will be 10. Let's check. So you can see it is 10. If I say search equals to v dot end, then it will return true, because it could not find that range. Same thing, it is basically. Oh, sorry. We need to just um, put it in brackets, I guess. So you can say it is returning true, that it did not find that thing. So now we will sort the sub vector as well. Okay, let's now try it. It will find the search iterator, so end will be false. So we should see the value 0. You can see the last value is 0, so it is finding the smaller range in the larger vector range. So that is our search algorithm. Now we will see find end. So let's put some values of the same range 12, 13, 14 in the lower part end side of the vector v. So let me put um, in location 6 and then 7 and then 8, 12, 13, 14. Okay. Now the find end should return search iterator find end v dot begin v dot end sub dot begin sub dot end. Now it will return us the iterator which is pointing to the sixth element. So if we see cout search iterator minus v dot begin, it should return us 6 because find end will start searching from the end of the vector v, not from the beginning, and then it will find 12, 13, 14 matching range starting with index 6, even though we have that range from index um, 10, 11, 12. So 0, 1, 2, 3, and 4 as well. Okay, we anyways are printing that vector. So let's search for we should print the vector here again. And let's see what find end returns. So find end is returning the index of this one because 12, 13, 14 is matching. So index of 12 is 0, 1, 2, 3, 4, 5, and 6. So 12, 13, 14 matching from the reverse side. Okay, so that is our find end algorithm. So now we need to complete with min max relative values. So searching for relative values, min element of vector v, cout star. Okay, it will simply return iterator to the um, minimum element of the vector. It need not to be sorted, right? So let's see what is the output. Oops, sorry. So you can see the minimum vector value is 10 because it is the first element of the sorted collection, right? So let's shuffle that vector. Shouldn't make any difference. Okay, now, and then of course the default random engine for shuffling, min element, max element, min max element. Let's try those three. Max element, min max element returns a pair, so we need to capture that min max pair, and then we can print star mmp first and star mmp second. It will simply return the combination of what min element and max element return individually, right? So we should basically see the same output. So you can see 10 and 19, min value 10, max value 19, min value 10, max value 19 for min max as well. Okay,